Hi guys, Erin here. This is the second video for this week where you'll be learning about between subjects design. In this video, you'll be learning about some of the main challenges that can arise when we test different groups of people, and we'll talk about some solutions to overcome these challenges. So just to review, between subjects design, we have a sample of participants that we take from the larger population, and we assign these participants to one of the different groups, one of the different treatment conditions, and we do what we can to make sure that our groups are as equivalent as possible. We then measure the dependent variable and see if there's a difference between our different groups. Here are some of the advantages of this design. What are some disadvantages? There's three. Let's get started and talk about them. First of all, it requires a relatively large number of participants and more than the within subjects design that we'll be talking about next week. So if you remember the law of large numbers, when we have, if we have two different treatment conditions and the rule of thumb is that we should have 30 participants in each condition, this would mean we'd have to recruit and pay for 60 participants. In that ADHD reading disability study that I told you about in the last video, we had 6 different groups. So technically, we should have had 30 participants in each group. We should have recruited 180 participants. We didn't recruit that many participants. The groups did not have 30 in each, and that was a weakness of that study. We had to frame it as a proof of concept study, a pilot study, and that other studies would need to replicate it to know for sure that our conclusions held. So, disadvantage, you need more participants. But we can do that. We can recruit more people. Let's talk about some of the other disadvantages. So with the between subjects design, different people are assigned to our different groups. So if you're assigned to one group, you're not going to receive the other group. And this means that each score is from a participant who may differ from other participants in lots of different ways. We call this individual differences. Individual differences are super interesting. They're what make us unique. That's what makes me different than my sister or than my kids or you, right? But they can also be a challenge when we are doing a kind of research design where we need to compare the average score between groups. And it's a problem for 2 reasons, or a challenge, I guess we should say. Individual differences can become a confound if our 2 groups are not equivalent. And if we have a lot of individual differences within each group, then it could potentially wash out or hide or conceal any differences that could exist between groups and make it harder for us to see that that difference really exists. So let's chat about them and we'll talk about some possible solutions. So let's start with the individual differences as potential confounds. Your textbook gives a great description of 2 fictitious participants named John and Mary that really couldn't be any different. John is a guy, has lower IQ, I think, than Mary, and John is also hungover when he comes in to do the study. Imagine John and Mary were participants in a study, an experiment that was, testing people's memory for advertisements. When you're looking at Google and there's those advertisements at the bottom of the screen, imagine you wanted to test people's memory for them depending on if they were flashy or if they're really boring. So you've got 2 different treatment conditions, flashy ads versus boring ads, and imagine we did a between subjects design where we have a group of participants viewing the flashy ads and a different group of participants viewing the boring ads. Now imagine it just happened to be that all of the participants in one condition were like John and all of the participants in the other were like Mary. Well, there's a lot of differences between those people. This could be a confound. Can you imagine if everybody was kind of hungover in one? This is going to be a problem. As an activity, a good way for you to make sure you understand some of the concepts, why don't you think about all of those different variables, ways that John and Mary differ in those descriptions in your textbook. Think about which of those variables might impact somebody's performance on a memory task, and see if you can list out which of those third variables, extraneous variables, could be a potential confound. And we'll chat about it at our next Teams meeting. So if we've got these differences between groups and participants in one group are noticeably different on an important extraneous variable that could affect the dependent variable, well, then those variables would be confounds. And this has a name, it's called assignment bias. This is a threat to the internal validity of an experiment because we wouldn't know whether any difference between our groups was due to the conditions that they received or those confounds. If we found a difference between how people's memory was for boring ads versus flashy ads, we wouldn't know if it was really the difference in the ads or the fact that all of our participants were hungover in one condition and they weren't hungover in the other. This is only a problem in a between subjects design when we have different people in our different groups. In a within subjects design that we'll be talking about next week, it doesn't really matter if you're hungover because you're going to be hungover when you're looking at the flashy ads, and you're going to be hungover when looking at the boring ads as well. So this is only a problem when we're comparing different groups of people. We have to make sure that our groups are equivalent in all of those variables. So this shows it in a graphical visual way. If you've got if all of the people just happen to, in one group, just happen to be older, smarter, faster, wiser, and than the people in this other group, then this is a problem because we wouldn't know if our groups are different because of whatever treatment they received or because of those individual difference variables. So assignment bias or confounding because of those individual differences is one way that we can have a confound in a between subjects design. Another way that we can have a confound is there could be difference not about the participants, but the environment that they receive. So let's say all of the people in one group were tested in a brightly lit, sunny room with nice music and aromatherapy, and we're testing their memory in this condition. And we've got the other group that are in like this dank, dark basement with neon lights, and the lights kind of flickering, and there's like a jackhammer going on in the next room. Obviously, this is a confound. We don't know whether any difference in their memory is due to whatever condition we're giving them or because of the environment. So a study with high internal validity is going to take steps to minimize both of these sources of confoundment. To know for sure that our independent variable is what's causing a change in the dependent variable, our groups should only differ in the independent variable. So this is why experiments are good. This is why experiments allow us to be able to establish that cause and effect relationship, because we're manipulating a variable and we have control over all of those variables. The separate groups must be composed of equivalent individuals that are created equally and treated equally. And if this is the case, then we can be confident that we've got high internal validity in our study, and that if we see a difference between groups, it's really because of our independent variable. So you need to think about this for your research proposal. If you're going to propose a between subjects design, then you're going to need to think and justify some of the rationale for how you're going to ensure that your groups are equivalent. So we've talked about this a lot. What are the three primary techniques to create equal groups? Well, here they are here. And you're going to have to think about what's going to work best for your study if you do a between subjects design. So random assignment, again, is just by relying on chance. We're randomly assigning people to different groups. This is going to be a good thing in that we're more likely to ensure that groups are equivalent on lots of different variables, but because we're relying on chance, we're not going to ever know for sure that groups are equivalent. So this may increase the internal validity, but may not. Whenever we can, we want to make a note of possible confounds and do what we can to make sure our groups are equivalent so that those variables aren't a problem. So any third variable that we think is going to impact our dependent variable, we should do what we can to make sure our groups are equivalent in that. One way that we can do this is by holding it constant, only testing girls, only testing boys. In the ADHD reading disability example that I gave you, we tested a limited range of kids. So we're only testing kids between the ages of 7 and 11. We're holding that constant. We're making sure that groups are equivalent. They've got a similar age. So this increases the internal validity, but the downside is it decreases the external validity. If we only test girls, we have no way of knowing whether our results are going to also apply to boys. If we only test kids between the ages of 7 to 11, we don't know whether our treatment's going to have the same effect for kids that are teenagers. The other way that we can ensure groups are equivalent is by matching the groups. So making sure we've got an equal number of girls and boys in each of our conditions. This increases the internal validity, but the downside is that because now we've got more variability within each group, it makes it harder to find a group difference. And I'm going to explain what I mean by that now. So individual differences can also be a problem when there is a lot of variability within a group. And this is a problem because it can conceal or wash out or hide any real difference between groups that really does exist and that is due to that treatment that they receive. It's kind of like noise. You can think of this as kind of noise, right? Like if you're talking on your cell phone and you go into a dead zone, all of a sudden it makes it harder to hear what the person is saying. Or say, sorry about that, or say if you've ever been at the cottage and you're watching TV and there's one of those old-fashioned TVs that need an antenna, and you have to like move the antenna or like stand in a funny way holding it so that you can get the signal. Maybe my cottage was just more old school than yours. Maybe you haven't experienced that, but it's not that the TV signal is not there. It's not that the cell phone signal is not there. It's there. It's just there's so much noise that it makes it harder for you to pick up. This is the same idea as individual variation that might exist within a group. If we've got a lot of noise within our group, a lot of differences between individuals in one group, then it makes it harder for us to know whether there's a difference between groups. So what we want in a study is a large difference between groups. If we go back to the music and art and how that impacts math example, if we really want to show that music makes kids better in math, we would want there to be a big difference between groups in terms of their math skills, but we wouldn't want a big difference within each group. So we would want people in the music group to be rather similar in their math scores and kids in the art group to be rather similar within each other so that we can show that there's a difference between groups. If there was a lot of variability, we've got kids that are really strong in math and not so strong in math, then it would make it harder for us to see that music improves their math. This is a major challenge for between subjects design. I'm going to give you an example with some real numbers, and I think it's going to really illustrate what I'm talking about here. I'm going to show you one example where there is a little bit of variability among individuals in a group, and we'll be able to see that it is easy for us to find a statistical group difference. And then I'm going to show you another condition where there's a lot of variability within each group and how this makes it much harder for us to show statistically that there is a group difference. So here we go. For this example, I'm going to go back to way at the beginning of the course when I showed you the back of my Sudoku book. And this idea that maybe doing Sudoku makes us sharp. Let's say we wanted to do an experiment to test this hypothesis. We wanted to know, does doing Sudoku actually improve your IQ scores? So you start a study here at Brock and you recruit 2 groups of university students, and we're going to randomly assign them to either getting Sudoku training or they're going to have some control condition. Let's say we got them just to type numbers on a computer screen. So they're still, working with numbers, but they're just not learning how to study the relationship among numbers. And we're going to measure their IQ before they get to training and after the training, and we're going to see if there is a difference between groups after the training. So just as a recap, you've probably learned this before. IQ is typically measured with some standardized tests where they have created it so that the average score that a 20-year-old receives is converted into the number 100. So the average score that 20-year-olds get is usually 100, and people will tend to fall within one standard deviation above or below that mean, that average. But for university students, you guys are smart. You guys are probably, above 100, and there's probably less variability. Most of you guys are probably within this range, right? There's not so many that are down here. So university students all tend to have relatively high IQ with low variance, not very much individual differences within a group. Let's see whether we can see a difference between people who are trained in Sudoku versus who are just typing numbers. So I just made up these numbers, but go with me here. So these are imaginary IQ scores before anybody got any training. This is our Sudoku group. This is our control group. I've just made up these numbers here. You can see that if we take an average, there's no difference between groups, and they're equivalent before training. That's a good thing. There's also not very much variance in the scores. The lowest score is like 105 and the highest score is 115, and that variance is similar between groups and it's not very big. So now let's say these two groups went ahead and did their training, and let's say Sudoku does help. And so I've added 10 to everybody's IQ in this group, and I've only added 1 to everybody's IQ here in the control group. It didn't really improve their IQ so much. Here you can see the average in the two groups. And if we do a statistic test to see whether that difference is statistical between groups, we do a t-test, and you can see we got this number here. This is the p-value. It's pretty small. Anytime the p-value is less than 0.05, we can consider it significant. So this one is 0.006. So we would be able to say, yes, there's a significant difference between groups. Doing Sudoku improves your IQ. Now let's say somebody says, well, you know, you only tested university students. That's not great for external validity. How do you know that your results actually would generalize to other people? Would doing Sudoku help the average person on the street? And so you say, okay, I'm going to do another study, and this time I'm going to recruit people from downtown St. Catharines. And everything else is going to be the same about my study. They're going to have 5 weeks of receiving either Sudoku training or our control condition. Let's see whether Sudoku training has the same effect on improving people's IQ scores. In this case, though, we've recruited people from downtown St. Catharines, so we're going to have much larger variability in their scores. There's going to be some people who are going to score really low, and there's going to be some people who score really high. The average is still going to be 100, but there's going to be a larger range, more individual differences. Let's see how those individual differences impacts our ability to see a group difference. So here's their IQ scores before training in group 1 and group 2. We've done a good job of matching our groups. They're equivalent. You might also notice, if you've got a good memory from a couple slides before, that the average is also exactly the same as our university students. The only difference is we've got more variability. The lowest score is 79, and the highest score, well, this person's really smart. They've got an IQ of 142. So we've got a lot of individual differences within each group. Now they went ahead and did their 5 weeks of training, and they learned the same amount as the university students. I've added 10 to everybody's score in this group, and I've added 1 to everybody's score in this group. Here we have our averages, and you may have noticed that those averages are similar to the university students. Now we go ahead and do a t-test and see, is there a significant difference between our two groups? And here we'll see that we don't have a significant difference. This number is not less than 0.05. This means that there is no significant difference between groups. The average is the same as our university students. They learned the same amount throughout the course, but because there was so much individual differences, so much variability within each group, that variability within the group made it impossible for us to see difference between groups. So just to make sure that we're all on the same page, a good way for you to see if you understood all of that is to, at home, answer some of these questions here, and we'll talk about it at our next Teams meeting. So this is for those of you who like pictures. I like pictures. This maybe can help you understand it as well. So here we have our, imagine this is histogram charts. This is the number of people, and this is their IQ in So average is like here and fewer people are over here. And this is our IQ in the Sudoku training group. And this is the average IQ, the IQ in our control group. And this dotted line is the average. And when we have low variability among people in each group, so that range is narrower, it makes it so that we can see a difference between groups, and this difference becomes significant. When we've got a larger range, more variability within each group, like we see here, this is much more spread out. Even though the average is exactly the same, we don't see a group difference because there is more variability within each group than the variability between the groups. So the whole point of a study is to show that there's a significant difference between conditions, but if there's too much variation within each group, then we're not going to be able to show that there's that difference. So what can we do about it? It's all great to say that there's all these problems. Let's talk about some solutions. We can deal with this variance. We can recruit more participants. We'd have to recruit a lot though to make up for this and to find a group difference. Remember that law of large numbers with, increase, but with diminishing returns. We can also do what we can to minimize variance, those individual differences within the group. We can do this by creating equivalent groups by holding that variable constant or restricting the range. So only testing people who are of high IQ, let's say, and looking to see whether there's a difference between our Sudoku and our control group. So this reduces the variance within the group, makes it easier for us to see a difference between groups. The problem though is that it decreases the external validity. In 2 weeks, we're going to talk about factorial designs and how we can have multiple different independent variables in the same study. And we could compare people who are high IQ, low IQ, Sudoku training, not Sudoku training, and this is a solution and a way to overcome this. So keep this in the back of your head. We'll talk about that more in a couple of weeks. What about random assignment and matching? We talked about that as ways that we can create equivalent groups. Does that help with our problem of large individual differences within each group? Well, no, not really, because with random assignment and by matching, having, similar numbers of people with high IQ, low IQ in each group, our groups are equivalent, but we've still got that problem of a large variation within each group. So this isn't a solution to minimizing the variance within each group. Finally, the other solution is we can do what we can to maximize the difference between groups in any other way. So even if we can't change the people, we can change the conditions. So we can decrease the variance within a treatment condition by making sure that everybody got the same kind of Sudoku training, let's say, and everybody learned the same amount. By doing a manipulation check, we can make sure that everybody in the Sudoku group is really learning a lot and make sure that they're getting the right kind of training to maximize our potential of finding a group difference. We can also sorry, that was the manipulation check. We can also decrease the variance within a treatment, make sure that everybody, I think I've just confused what I've just said there. I'm sorry, it's late. And I don't want to record this again. So I'm just going to say this again. So we can decrease the variance within a treatment by making sure everybody in the Sudoku is getting the same kind of Sudoku training. And we can also make sure that people in the Sudoku group really learned the Sudoku by doing a manipulation check and make sure that nobody in our control condition learned any Sudoku, maybe by learning about what the study was. So we'll talk about that in a second in terms of communication between groups. So there's two other threats to the internal validity of between subjects design. Let's talk about that and then we'll wrap up this video. Attrition is a threat when people drop out of our study. This is always going to happen. People are free to participate and free to stop whenever they want. This can only be a problem if more people drop out from one group than another, because then our groups are no longer equivalent. So this is what this might look like in a picture. We've got people in, assigned to 2 different groups. If we've got more people dropping out of this group than this group, this would be differential attrition. Now, to show why this is a problem, let's go back to our example of music versus art training. If we had started with 30 participants in each group and half of our participants dropped out of the music training, this might be a problem because the people who drop out might be different than the people who persevere with the training. It might be that the people who drop out really don't like music, don't like working hard. The people who stay in are, really keen to learn a lot and really keen to work hard and learn how to play their instrument. And so they may end up getting better math scores because of those personality differences. So there's nothing really you can do about this, except you need to be honest in reporting how many people have dropped out of your conditions and whether those people who dropped out might be different than the people who stayed in. Finally, the communication between groups can be a challenge because it can make that difference between groups larger or smaller. So groups might become more similar if, let's say somebody, remember that Sudoku, if somebody in the control condition learned about what the people in the Sudoku training were doing, then that obviously is going to make it so that our groups are not as distinct as we would want them to be. Groups can also become more different if they find out that somebody in the other group is doing something that's more fun and they're like, hey, I want to be in that group. I'm just not even going to participate anymore. This is why it's so important that if you compare 2 groups and you've got your treatment group and a control group, that your control group has something interesting to do too. So to summarize everything from this video, there's pros and cons of everything. The pros of a between subjects design is that, we can address many different research questions and we don't have to worry about people so much so as a within subjects design, learning what happened in one condition and transferring that over to their other because they're only getting one condition. The 2 main disadvantages are that we need lots of people and that individual differences between participants could be a potential confound if we don't create equivalent groups. And individual differences within a group can also be a problem because it can obscure any difference between groups. And we talked about some solutions to both of those. Thanks so much for listening and hanging in with me here. We'll see you next time.